Okay, we're going to look more about this ARM state machine, just go through and review it a little bit. I hope that you found when you did your quality assurance little quiz that you understand what's happening here and how these states are working. Let's just make sure that we go through this and we understand what these states are. Understanding the states are going to be it really helps out. This is basically a when we're vertical and not moving. So this is that the arm is in a safe position. It's not hanging outside the robot, and it's also the place that we start. Once the operator says, I want the arm to go down, we move to this state, which is actually, this is the arm moving from vertical to horizontal. It's going to continue to do so unless the operator takes her finger off the button on the gamepad, and therefore it becomes unpressed, and then it needs to go back up. Okay, this is the going back up here. And by the way, I think this is a dandy way of doing operator control because suppose that the operator wishes to put the arm down, let's say, to grab something. Okay, and then what happens is another robot gets close, and so she becomes afraid that the other robot's going to break the arm. All she has to do is take her finger off, and then that arm goes back up through going through this state to a safe position, returning back over here. So this is a great, I think that's a great human factor interface. And so let's go back here. This is when we're going down. This state looks a lot like this initial state. So state 2 looks like state 1. Why? Because we're doing the same thing. This was the vertical state. This is the horizontal state. This is the transition state now. State 3 is the transition state from the horizontal state back to the vertical state. And so this is a neat way to draw it. Some people don't like drawing these things. So what we're going to do is we're going to look for another way of drawing or representing this, and it's called a transition table. So let's go through and look at a transition table. By the way, we saw one of these in the very first example that we did in the first video when we were just lighting a light with a switch. Here is a state, and that's called state 0. Okay, its output is 0. This reads not pressed. So press with a bar over it is not pressed. And then pressed without the bar is, of course, pressed. We don't look at the encoder, so we say not applicable, or NA, and then we will talk about the next state. So when we're at state 0, we remain in state 0 as long as the switch is not pressed. That accounts for this little loop here. When we're in state 0, we go to state 1 when the switch is pressed, and that's the transition out over here. So we can now build one of these little pieces for every one of the states that we have. So let's do for the second state. The first state, which would be state 1. Okay, convince yourself that this is state 1. The output is positive because we want the motor to be rotating the arm down to the horizontal position. And these tell you what the encoder values are, or what the switch position is and the encoder value position is to go into the next states. Okay, so this completely describes this figure because this arrow goes to state 2 and this arrow goes to state 3. Okay, and so you understand the equivalency between that diagram and this compound row of a table. We would do the same thing for the other states, and we'd end up with this. So this state machine, okay, it describes exactly what we had when we had the circles. And so you can see the states, you can see the outputs of the machine. When we have those states, by the way, there's a negative sign there. It's a small one. We can see how the switch and how the encoder affects the transitions to different states. So some people like this better. Okay, use whatever form you want. Okay, Now, I think there's some general comments before we finish this one and move on to some other stuff. Okay, hardware and software must really talk about rotational directions of positive and negative motor power. Don't assume it. And especially this becomes confounding when there's gearboxes between the motor and the arm or the thing you're moving. You have to test it. And so software and hardware need to get together and provide a very simple, very safe test that very slowly moves the arm so you can understand which direction the arm moves under what power. The encoder values are also things that you're going to have to understand. Nobody's going to give you an encoder of 72 and 562. Okay, it doesn't work that way. So you're going to have to experimentally determine the encoder values that you want. Okay, now here's the trick. The encoder value is generally 0 when the robot's initialized. Okay, so the value of 0 indicates the position of the arm when the robot turned on. Okay, now some teams require the pit crew, okay, to manually position the arm to a very specific position, so they know that that position is 0 because that's what the encoders are going to call it. Okay, now if the pit team, and by the way, when the pit crew, these are the guys working on the robot with you, do not set the arm correctly, you get a disaster. Okay, because all of a sudden 0 is not vertical, 0 is something else. Okay, and then when you change your software to run, when you run your software, you'll drive the arm either below horizontal or beyond vertical, and that could break the arm depending on what's behind there. You have to have there's really neat, robust methods for coordinating this for understanding what the encoder value is. Okay, and that requires active initialization. Okay, and that's for another discussion. It's not part of this. Okay, and so the other thing that this example doesn't do, it's not robust. This is a very simple example for you. Why isn't it robust? Because it doesn't account for errors. There's all kinds of things that can go wrong with an arm. Suppose you have an arm that you have the motor driving a power, but the encoder's not changing. Well, what does that mean? That means either the encoder's broken, so you can't use the encoder to drive this, and you better figure out what to do about this arm before you break it, or the arm is stuck. It's tied up in another robot. It's tangled up. It's on top of another robot. And so you need to figure out what to do with conditions like this. So when we actually do a design, you look for the unusual conditions, you look for the initial conditions, and you make sure that your design is robust. A very, very important word. Okay, let's take a break before we go into software considerations, and we'll take it from there. I hope you now understand what state machines are and how to use them. You won't really understand how to use them until you actually do them yourself. Okay, and and then so take the quality assurance and make sure that you understand it. Remember, you can always go back and revisit the video that you just watched if you have questions. Better yet, visit it with a friend.